Hello everyone, and welcome to this short-term course on viscoplastic self-consistent crystal plasticity modeling. This talk will be given by Dr. Carlos Tome from Los Alamos National Lab. He is visiting IIT Bombay as a distinguished visiting professor, and we will be having this course over the duration of this entire week. And this is a very hands-on course, meaning that in the first couple of days we'll be going over the theory of self-consistent crystal plasticity modeling, and in the next 3 days we'll be doing a lot of hands-on examples. So we want all of you to if you want to take some meaningful things back from this course, we want all of you to bring your laptops and install the VPSC code. We have circulated all the instructions with you, and if you are facing any issues, will discuss with you. We'll be happy to help you after the class today. So without further ado, Carlos, you can get started.
This course is based on a book that This course is based on a book that is going to appear very soon. That we have written with my collaborator Ricardo Levenson, and some of the examples that I'm going to be showing during the course are sold there. The book is going to be distributed together with the code in the input and output file, so you will have access to that. However, you do have access to the code and the example files as part of the package that was distributed to you. So we are going to be relying on that for this particular course. We are going to be providing with the notes of the course day by day, partly because I'm still finishing the last couple of days of the course. So day by day, by the end of the day, we will post. If you need or want to have some personal interaction, as Anirban mentioned, we are going to be available for that at a place to determine, but you will be able to make consultations or ask questions in the morning or later in the afternoon. For those of, I hope that you guys have downloaded the software that was recommended, because we are going to need it to run the code. For those of you running Windows, there's no problem. For those of you running Linux, there is this issue that in Linux the notation for the folders and subfolders have the slash, the forward slash, while in Windows they use the backslash. So you will have to change that in the input file. The other problem is the uppercase and lowercase, which we really were not completely consistent with, but you may find that's a problem with if you're running Linux. So take that into account. That requires a few changes. It's not a big deal, but I mentioned that to you. Today we are going to start to break ground with running one of the Fortran calls, so we see how things work, and if you guys can manipulate things, and if I'm communicating what you need here. This is the code pol8, which is a code to plot pol figure. So without much ado, I'm going to get started with the course. The first part has to do with the concept of texture and polycrystal. So you are familiar with the polycrystal. The polycrystal is an aggregate of atoms. Usually, the solid materials start from the MEMS, and the crystals start rotating and solidifying. They grow, and when they grow with different orientations. So that distribution of orientations is what we call texture. And there are different ways of describing texture. I'm going to mention pole figures and inverse pole figures. Now, in order to represent texture, you have to represent the system, the crystal is defined with respect to how it sits in the sample. So, if you see that your crystal has these three axes, crystal rotating with respect to the sample by doing three consecutive rotations. So first is a rotation around the axis 3 by 3-1, then a rotation of capital P around the axis 1 here, capital Phi, and then another rotation around this axis by an angle phi2. So those three angles define what is the position of the crystal with respect to a reference system. The orientation distribution function tells you what is the volume fraction associated with each orientation. So it's a continuum function that f function of the three angles. This is a three-dimensional space, and so by associating an intensity with each point in that space, you are telling what is the concentration of orientations. And because it is a three-dimensional function, it is usually plotted by making sections in the phi1, phi2, and phi space. You take sections in that space of equi-intensity lines, and then you will usually see it plot in this way, those sections. We are not going to be really working with this in this course, so I'm just mentioning that so you are familiar with that representation. What we are going to be dealing with is pole figures. So here I'm coming back again to how you represent a crystal with respect to the normal direction, rolling direction, transverse direction. Here are the three Euler angles that I mentioned previously, and because a vector is a tensorial quantity, we can rotate the vector from one system into the other. In truth, we rotate each of these axes, we rotate each of the axes into the other axis, or we have a linear transformation that, given a vector in the crystal axis, R, well, in this case, in the sample axis, this matrix R gives you the components of that vector in the crystal axis. The form of that R matrix is this one, and this is what is programmed in the subroutine Euler in the VPSC code. In the VPSC code, R is really called AG, A of the grain, A of the grain. So how do we represent textures using pole figures? Well, the pole figure is an easier concept to grasp for representation of textures, but it is not any univocal representation, so it's a bit tricky. But essentially, if you have your crystal, imagine that you have your crystal at the center of a sphere, and the main axis of the sphere are those sample axes, the normal direction, transverse direction, and rolling direction. And say you want to represent the 1, 0, 0 planes, although you can represent any set of planes that you want. But let's say you want to represent the 1, 0, 0 planes. So you project the normal of those planes, which there are three of them in the cube. You project the normal until it intersects the sphere. And so now you have 3 points on the sphere, and then if you flatten the sphere or look at it from above, let's say, then you have 3 points here representing these 3 axes, okay? And if you have now many points, you can represent the density of points using intensity lines, much the same as we do with the weather maps that represent temperature or winds. So these lines are lines of equal intensity, meaning that the volume fraction of material, this is the volume fraction of material represented by this intensity line. So this is a typical rolling texture. As you can see, I'm plotting here these 1, 0, 0 planes, but now in this texture we have 500 orientations, so there is 1500 points here. So this is what it looks like if you represent points. And this is what it looks like if instead of the points you represent the density of those points. So this is the point representation of the pole figure. This is the intensity line representation. The point representation can be misleading because if you have many points in one spot, you cannot tell if the intensity is high or not because they fall one on top of each other. So you have to be careful with that, and that's why here what we are going to do is we are going really to work with the intensity line representation of pole figures. So the way in which you project those points is called, why is it called a pole figure? Well, as I said, if you imagine a hexagonal crystal like this one, and say you want to represent the z-axis, that is the basal plane of the hexagonal crystal. So you put your crystals at the center of the sphere. Here I'm using only 2 crystals for this example, and then you project the normal until it intersects the sphere here, and it intersects the sphere here. And from this point in the sphere, which is one of the poles of the sphere. From this point, you trace a line that goes through this intersection to a two-dimensional plane. So the circumference of the sphere projects here, and each of these points, one projects there and the other projects here. And so in a flat representation, these basal poles will be represented by these 2 points here. So that is a pole figure of this bicrystal. Now, I showed you before the 111 planes, the 100 planes. This is the representation of the texture for a material that has been rolled. So a material that has been rolled, this is a cubic material, which could be copper. It has been rolled, and the texture, the 111 planes have this appearance, the 110 planes give you this appearance, the 100 planes gives you this appearance. So there is, from here, the problem is that I said that there are three 100 planes in the cubic crystal. So each of the grains will give you 3 points. But if you look for 1 point here, you cannot tell where the other 2 points of this grain are. They can be, I mean, there is a rule, they have to be along a circle here, but they can be, any 2 points that fall along that circle could belong to that grain. That is what I mean when I said before that the pole figure is ambiguous, and the inverse pole figure is unambiguous. Sorry, not the inverse pole figure, but the distribution function is unambiguous. So there is a concept that is inverse pole figures. So in the case of inverse pole figures, you take as a reference the crystal. So you say, I'm going to represent, for example, an axis, the tensile axis, in an experiment where you do tension. I'm going to represent the tensile axis in the axis of the crystal, the 100, 010, 001. And because all these six triangles are equivalent as far as pulling along this line. The tension along this line will do exactly the same effect as all the symmetric positions of this tensile axis. You only plot a fraction of the sphere. You only plot the fraction of the sphere, and that fraction, in the case of the cubics, has this appearance. So here you plot between the 111, this one, the 101 and the 100, you plot the position of the tensile axis. And when you do that, in this case, for a material that has been like copper that has been deforming tension up to 100%, what you see is that the tendency is for the tensile axis to appear here. In reality, what is happening is the grains are reoriented in such a way as to position themselves with respect to the tensile axis with the 101 direction aligned with the tensile axis. That is in compression. If you do tension, the tendency is for the grains to orient the 111 direction with the tensile axis and the 100 direction with the tensile axis. So those are called texture components. This is a texture component, this is a texture component, this is a texture component. And this should be the equivalent plot using dots. So you are going to do this example and the previous example today as part of the use of the code POLE. This is not so relevant for everybody, but it is common in the metallurgical trade to identify the raw material by the texture components that they exhibit. So different texture components have different effect on what you want to do with that material. For example, the steels for transformers have to have they prefer the 111 axis oriented perpendicular to the sheet, or for some forming operations you want other components, or you don't want those other components because they may lead to localization and breakage. So it is common in the metallurgical industry, especially for the cubic materials, because those are the ones more used, like steel, copper, aluminum, to identify ideal orientations. And those ideal orientations have been identified as copper, brass, S, GOS, and Q. And what are those ideal orientations? Those ideal orientations, which are shown here, for example, if you look at copper, the 100 of copper, there is a point there, a square square there, there's a square there, there's a square here, there's a square here. So you have these three squares, or these three squares. If you look at the Gauss orientation, which are the circles, you have this circle here, this circle there, this circle there. So those orientations is what are used for characterizing the outcome of a rolling process. The way in which they are identified is by which is the plane that is aligned with the normal direction. So, for example, in the cube case, the 001 plane is aligned with the normal direction, and which is the direction in the crystal, the 100, that is aligned with the rolling direction. So that is how they are identified, by which one is the plane and aligned with the normal direction, and which one is the direction aligned with the rolling direction. And here you see how each of these ones are identified. Now, this plot here is a plot that eventually you will be able to calculate in one of the examples. That is how these components evolve as you keep deforming your material. And as I said before, the idea here is that for metal forming, you want to control some of those components, and then what you want is either to increase them or to eliminate them. But first, you have to characterize those components. And here, as a function of the volume fraction associated with those components is plotted as a function of the deformation in a roll FCC crystal. So the deformation here is 63% reduction. That is the epsilon 33 equal 1. And you can see how each of these components evolves. At the beginning, you have they are all less than 10%. If you have a random polycrystal, there are always going to be some components that fall within those orientations, and they don't fall exactly. I mean, usually the criterion is if they are 15 degrees within that orientation, you count them as a component. And but then you can see that, for example, the S component increases a lot. So that, as I said, if it is good for what you want to do with that piece of steel, that is good. If not, you have to try to get rid of it. And so you can see that the tendency is for many of them to increase as you increase rolling, and as you end up with the texture that I showed you before. So this is also something that you are going to be doing maybe tomorrow when we go through the examples, calculate the evolution of these components as part of a rolling simulation. Okay, so here we come to a point. We are going to do a dry run, see if you can run the plotting code that we distributed. I'm going to explain here the input and output files and the procedure. So if you have your computers, you don't need to do that as I speak, but I'm going to go through the slides, and then we will see if we can go again and you repeat the different steps in that process. Okay, so the code is called Pol8, and 8 comes because it's the version 8 of the code. It allows to plot Pol figures or inverse Pol figures from one or several discrete texture files. The main file there is the pol8.in, and in that file you are going to be given the information that is needed with the parameters for the plot. The files required to compile and run the code are pol8.4 and pol8.dim. Those are in the package that we distributed. In the package that we distributed, there is a folder called Pol8, and you should go into that folder. The code is there, but the executable is not distributed, so you will have to compile the code. For that reason is that you are going to run a batch file which is called compile Pol8, that should be in your folder, compile Pol8, and that file essentially is a G-Fortran compiler. And these are some switches that have to do with telling the code what has to do or what has to ignore. But essentially, what you tell, use G-Fortran to compile Pol8.4 and create an executable that is called Pol8. So after you compile, you will have an executable called Pol8. So as I said, with that you are going to plot Pol figures or inverse Pol figures. You will run the executable Pol8 from the DOS window. Is everybody going to be using Windows, or someone is going to be using Linux here? Let's mention what could be the change that you need to do. But you will be prompted when you run the code. You will be prompted to enter a five character label for the output files, and that is meant to be able to save those files for later plots or to distinguish different cases. If not, if you always have the same name for the files, they get overwritten when you run the code for other problems. So the idea is that you label them with 5 characters. For example, the 5 characters could be run number 20, run 20, okay? And then the plotting parameters are controlled by the screen entry default as follow. And this default allows you to 3 different choices for what type of plot you are going to do and with what parameters. So you enter default 1 if you want to choose the settings, which requires really expertise and knowing the code, because there are several parameters in the code, and they are if not, they are assumed hardwire, those parameters. 0 is the one that you are going to be using, and only a few parameters need to be entered if you run 0. And then if you enter -1, you will read the settings from an input file called polay.pro. I'm going to be describing this file. So then, in order to plot the pole figure, so what this code will generate is a bunch of output files that you can plot with any plotting software. That could be nuplot, and the reason why we put nuplot is because there is a batch file for nuplot that will allow you to run instantly the pole figures, to plot them instantly. But you can use Excel or Origin or any other plotting program. And you will enter the command start nuplot in the DOS window, and this will open a new DOS window for nuplot. And in that window you enter load, run20 plt, run20 is the file that you just created, and this will display the plot. So, as I said before, Polate uses the 4 parameters. A few can be entered through the console, or it allows to choose all parameters. In the package that you received, in the folder Polate, there is a manual. So there is a manual with a description of the code and all the parameters with examples. So when you have time, or if you have interest, take a look at that for a more in-depth understanding of what the code can do. No? But essentially, after you make a run, the code Polate will create this file, polay.pro, and this file will look something like this, where the values of all these parameters will be given here, and here you are indicating how many levels of intensity you want in the plot and what values are you going to assign to those levels. So you plot intensity points. By the way, random corresponds to 1 in texture representation in pole figures. Random corresponds to 1. Anything below 1 is below random. Anything above 1 is indicating that there is a texture component. So the first example, and this is the one that we are going to run, is plotting the rolling pole figures that I showed before. So you will have to go into the example 1 in that subfolder Polate, and there is a polate.in file. You have to copy that file in the root directory. So, and the file will look like this. So you can plot several textures at the same time. So you say how many texture files you are going to read. In this case, it's only 1. Where is that file and what is the name? That file is in example 1, FCC roll text. Do you want to plot a pole figure or an inverse pole figure? The pole figure is 0, inverse pole figure is 1. And what are the dimensions of the single crystals? It is important to give the dimension, that is the length of the axis in the single crystal and the angle between the axes, because the position of the planes depends on because your planes are given in the Miller notation. This is not a problem with cubics, but if you move away from cubics, 111 doesn't mean something at 45 degrees, for example, in the hexagonal material. So you need the dimensions of the data file, and this file, which we call the single crystal file, is really the same file that we use in VPSC, except that we only use the first 4 lines, of that file. The rest is not necessary, not needed. Then you say, okay, how many poles you want to plot? 3 in this case. And what are the Miller indices of those plots? 100, 101. Okay, so this is what the polay.in file looks like. Eventually, I would like you to play a bit with these things and see what you get. Change some of these parameters and see what you get. And then what you should get for that particular case is a file like this. It's a plot like this. Now, these are really 2 runs. You get either intensity lines or dots. So as I say here, in the first run, choose to create an intensity line per figure. That choice is when you run the code, it will look here for 0 or 1, okay? So you will have to run the code twice in order to create either intensity lines or dots. In the second run, choose to create dots. The other choice that you have is to choose where you are going to put the axis of the sample. So in rolling, axis 1 is usually the rolling direction, axis 2 is usually the transverse direction, and axis 3, which is in the center, is the normal direction. So that is the usual way of plotting. But you can really choose any permutation of this axis. You can even use negative values. And so instead of 2, you can plot -2 here, for example. So this is something that you have to choose, and this is what you should be getting. So this one I'm going to explain, but I don't think that we are going to be doing that as part of the exercise. I will leave that as an exercise for you to do later. For Linux users, there are two changes for Linux users. As you can see here, and this is a good example anyway, this file, FCC compression texture, which is the name I gave that file, you can give it any name, is in the subfolder example2. As you can see, the subfolder example2 has a backslash here. The Linux user will have to put a / here. So whenever there is a backslash, put a /. And the other thing that you need to make sure is that go into the folder example2, look for this file and see if the uppercase and the lowercase are consistent with what you put here. If in the folder they are in uppercase and you enter this, Linux will not find that file. So you will have to go into the folder example2 and see how the file is named with uppercase or lowercase and use exactly the same name. So that is the only changes that you need to do, both in the input file, in the data files. You have the FCC single crystal, the same story, / and making sure that the upper and lower case are consistent with the name in the folder. And this is also true for when you run the VPSC code. The VPSC code also has input files that look a bit like this. They are a bit more complicated, but they look a bit like that. You also give a list of what are the files that the code has to go look for in order to run a simulation. So in this particular case, we are going to give the example of those inverse pole figures. There are practically no changes to this file. In this case, you are going to be plotting two files at the same time. So you have two files, tension and compression. They are going to be plotted simultaneously. And you choose one here for the inverse pole figure. And now here, instead of Miller indices, you have to put the direction of the axis that you want to plot. Usually you plot either the axis 1, the axis 2, or the axis 3. So you usually plot 100, 010, or 001. So you are plotting the axis 3, which is the tensile axis in this particular case. And this, I showed you already, these inverse pole figures. This is what you should be getting using intensity line plot option, which I representation equals 0, using dots option, I representation equal 1. As a rule in my code, I use 0 as the defaults for parameters. Usually 0 are the defaults for running the code, and other values are the non-default. So I think that we are going to stop here. We are going to go through that example of plotting the rolling texture, and then we will continue. So I would say, okay, if you haven't yet compiled the code, follow these instructions, find this file, compile pol8 in the subdirectory pol8. Actually, I think it's called pol8d in the package that you received. File this file, compile pol8, and see if you can run that file, and if it gives you an executable. Yes, if you go to example 1, for example, so you are going to see this file pol8.in. So you copy this file in pol8d. Then you open the command window, pol8d, and you run compile pol8. So it runs So as you can see, it created a file pole.exe. Can you see my, yeah, kind of. It creates a file pole.exe. So I'm going to look at what is this file pole.in. I'm going to open it just for you to look at it, but as I said, this is FCC role text, so it is going to be pointing at that one, which is this file, FCC role text, so the rolling texture. And so in the code, I'm going to run the executable, collate, and it asks for the identification of the output file. So I'm going to put out pt, and then here is where you have to choose the settings. So 0 is what I suggest you to do, because yeah, 0 is what I suggest you to do here. And then it asks you, enter the indices of the pole figure axis. So you enter whether you want what you want to have. So what axis you want here, if you want the axis 2, 1, and 3. So you enter 2, 1, 3. It will ask you for an option of symmetrization. As I say, 0 is the default, but you can symmetrize this pole figure and take this as a mirror plane, in which case whatever is here is going to appear as a mirror there. Or you can choose this as a mirror, so whatever is here is going to appear as a mirror there. Or you can use both simultaneously. You also have the option, if you do this, you have the option of plotting only part of the pole figure, because the other part is symmetric. So you can plot this, or you can plot this. Now these are all these options that I was talking about that you can play with. Or you can decide to plot only this part of the pole figure if it has both symmetries. Okay. In this case, I'm going to pick 0, just not to force a symmetry in it. And this has created a file called rolling PLT that I'm going to process now. Now, the other thing that you plug in, I don't know if you can see it there, but it makes the statistics of the grain weights. What is the weight assigned to the grain? Because these files contain a certain number of orientations with a weight. In this particular case, all the weights are the same because it's a random file. But you have the choice of cutting down the number of orientations and leaving only the ones with higher weight. So that is another option that you have. And so that gives you sometimes a much cleaner pole figure, showing you only where the maximum intensities are, which is what this statistic is showing here. As I said, all these things are options in the code. You will have to take a look at the first pages of the manual. It's not long, and you can play with those things. So once here, what did I call that? Out, no? Yes. Okay, it created all these files, but out of these files, these are the files that you are going to import into your plotting software. The one that is used by GNU-plot is only outpt plt. That is the one that is going to be imported into GNU-plot. All the rest of the files contains the coordinates. Yes.
Because of that, GNU plot, when I load, compliance for that file name, but if I manually remove that space and give the space after that for using, it works. Yeah.
It never happened to me, but no, it's good to know. Maybe it is some character.
If I correct, I do get the plot.
Yeah, perfect. So if you just make 5 characters dot plt, it plots. Well, maybe because you are using Linux and maybe it adds. Yes. So, but it's good to know. No, I don't use Linux myself. You use Linux, no? Have you come across that? Well, anyway, if here you say start new plot in this window, it will create a window, a new window with a directory new plot. And I know that you can run this from Windows directly also. I mean I'm accustomed to run it from DOS. You can run it from. And then at this point you say load out pt dot plt and you get you get directly the plot. So these plots, this program needs a bit of improvement with the labels. The labels are a bit messy. So this is not what we use for publication. But one can really, one works a bit on getting the labels in the right places. You can use this for a publication. So that's essentially the sequence.